Okay, good morning. How's everybody? Tired. I'm also tired. But it's a good day. We're gonna continue where we left off on Monday. This one gets me every time right here. Like if I have a class that's like I'm not paying attention to, or it's maybe I think it's the easiest, I'll end up doing the worst in it because I'm not paying attention. I find that stressful. I also prefer this class. This is like, you know, this class and another class, there's only two I teach. I prefer these two over all these other classes this semester. 3-hour bio lab, is that true? That's long. Wow. That's a lot. Same in chemistry? That's also 3 hours? Wow. Would you like to have a 3-hour math lab? No. No? Okay, well, just checking, you know, we could add that. Okay, so I think, yes, it's time for the mini quiz. So you can talk to anyone you like, but no technology, right? No phones, no laptops. No, we're taking little Apple Watches, although I don't think the answer is to be on your Apple Watch. Please grab some and tap them back. Same here. Remember, you can talk to anyone you like. At your table, not at your table. The more you talk, the better. Oh, can I have one of those? Oh, sure. Yeah. Hey, let me give you a quiz. You can talk to anyone you like.
said A.
No, I said A.
All right, don't forget you can ask your neighboring table because we're about to collect them. Yeah. All right, you ready to hand it in? No? You want one more minute? All right, one more minute. Usually I like not this. It's okay. All right, that sounds quiet. Please hand them up. Oh, thank you. This album. This one.
I think it's A.
Thank you. Any more? Okay. So what do you think the answer was? Who thinks A? Oh, that's okay. That's a very strong A. Let's see if that's true. I wrote them here in fancy language. These are the same things that you just looked at. I just thought it would be fun to write it with the upside down A's. This line is pronounced such that. So that's what this line is. So the one you're saying is true is that for all X in the real numbers, there is some Y in the real numbers such that Y equals X squared. This is one of these that's like a game. For all X, there exists Y. So you tell me any X you like. What X do you like? One. And I will pick, I'll pick 1 because 1 is 1 squared. So in the back, someone pick another X. 4. So you pick 4, no matter what you pick, I can find something that's the square of your number. I'll pick 16. If you pick -4, I still pick 16. Okay. If you pick 0, I'm going to pick 0. I can always win this game. Okay. So A is the one that's true. Does anyone want to add? I wrote these in shorthand, but I can pronounce them out loud if you like. Anyone want to ask about these 3? The last one? Yeah, this one says that there is some X out there such that every real number is bigger than that X. There's some number such that every real number is strictly larger than that X. It's like it would be like saying there's a smallest number. But in the real numbers, there isn't a smallest number because there's negative numbers too. Even if I made these greater than or equal to 0, I would need to put a greater than or equal here to make it true. Because I need that every number is strictly greater than the one you picked, including the one you picked would also have to be greater than the one you picked. Anyway, this one is false because there is no such X that every other Y is bigger than. So that one is false. Anyone want to ask about the other 2? Okay, great. Great. So let's see. The question of the day has been flipped to ask or answer. I haven't been getting a lot of questions this way recently, and I think it's actually because people just ask them out loud, which is fantastic. But I just want to keep reminding you this is here. One thing I would like to hear your questions about is how to get help. So like if you have a question about how to use some of the resources or go to one of the sessions or how SMLC works or any of those things, that would be a good thing to answer here. And I'll answer those questions as they come in. And in particular, why isn't the sheet that I thought was going to be here? Here, hold on a second. I put something, because I put it at the end. I put it there. Okay, yeah. So ask me questions about how to get help, and we're going to talk about that at the end of class, okay? But that's a good thing to ask here, or anything you like. Okay, yeah, I'm sorry. I had things out of order in my brain. Okay, so we're done with tricky logical statements for now. We've done plenty of them on Monday and now today, and you've been doing a bunch of them on your homework. The second thing in this section is about proofs. Now, those sound scary, and some of you haven't seen them since geometry. You remember those proofs where you like make a T sometimes or a list, and each statement had to have a justification, and you had to prove some geometric fact based on other geometric facts that you could establish. Well, I don't know why you only learn that in geometry, because pretty much all of math is about writing arguments for things. So we're going to start getting used to writing arguments for things. So for example, let's say I wanted to prove that if A and B are odd, then A plus B is even. So like, for example, if A was 3 and B was 5, those are both odd, right? What's 3 plus 5? 8. That's even. Okay, I proved it. Did that prove it? Proved it for those particular ones. But this statement is basically asserting that whenever you have, and the universe here is integers, it doesn't say that here, but it is. Whenever you have two integers that are odd, when you add them up, it's even. So if I get like the integers -5 and 11, when I add them up, what am I going to get? 6, which is even. Have I proved the statement yet? No. I've shown 2 examples that show that it's true. But the statement is true for infinitely many pairs of odd numbers. And I need to make an argument that argues that no matter what 2 odd numbers you have, the sum will always be even. Now, do you actually believe that? People, you're like, oh no. Yeah, that's a good answer. So you do, who believes this fact? No. I mean, I wrote it here, right? Would I write it here if it wasn't true? You should sort of believe it. But like, you believe it, believe it. Why do you believe it, believe it?
I don't know. I can't think of a number that doesn't fit it.
All right, you tried lots of examples and you couldn't think of one that doesn't have this property. That's good. What is it like about 2? What is an odd number anyway? What is it?
Not an even number.
Not an even. Okay, what's an even number?
Not an odd
Ah, you can't do that. Yeah, an even number is evenly divisible by 2. That's where the even comes from. So it's 2 times some other integer, right? So if a number is even, it's 2 times some other number. Okay. Okay, and then odd number is going to be not even. Okay. But it also means that if you divide it by 2, you have 1 left over. So odd numbers are always like 2 times another number plus 1, right? 5 is 2 times 2, and then an extra 1. There's an extra. You know what I mean? If it's odd, there's an extra bit. So you got a number with an extra bit and a number with an extra bit. When I say it that way, are you starting to believe this conclusion? Yeah, why?
Because those extra bits make it even.
Yeah, those 2 extra bits, they'll get added together and sort of just put another 2 in the mix, and you'll end up with something even. Okay? That's what the proof actually is of this theorem. We just have to argue it a little more precisely. That what I did was literally called a hand-waving argument, where I talk about bits and then you believe it, right? But we have to actually write it out so that anybody reading it could agree that this is so. So what I've done is for your first proof, because proofs are hard and we will be doing them on and off in this class, so it's good to get used to them. I've cut the proof up and put it out of order. So if you look at the first part of this worksheet, well, that's a lot of them for some reason. If you look at the first part of this worksheet, the part on the top, these are all the sentences in the proof. These are these are like 3 different lines here. It's hard to tell. And these are 2 different things here. So sometimes it's hard to see. I want you to try to put this argument in order. So try to write an argument, and these are the pieces, and try to write it in order with your table. And I'm going to bring up a little slidey thing where we can move stuff around. So go ahead and start talking about that. Huh.
That's probably actually.
Huh. Can't find the board I was going to push things around on right now. We could. I have a whole activity about that. If we get bored, we can argue whether a hot dog is a sandwich. That's basically what that activity is. That's awesome. There it is. Here's my stuff. Okay. All right. I started to worry a little bit. I couldn't find my thing. Okay. Did anybody have an idea what the first line should be? Like, look at this list here. Which thing do you think comes first? I like that. Suppose they're odd integers. That's kind of where we start, right? We start by supposing that we have 2 odd integers. So on my copy, these things should actually move around. Let's see if that happens. Okay, so that's going to be first. And I'm going to put proof up here. This is basically the only thing I miss about working online is that y'all could be in breakout rooms moving these pieces around, but you'd also not be speaking to each other. So I think this is actually preferable than doing that. It's really hard to interact with a breakout room. Who had a rough year last year at breakout rooms? Yeah, I did too. I thought I was going insane. Okay, so A and B are odd. Figure out what comes next. What's the next line? Just think about it at your table for a minute. My hint for you is you've just said these numbers are odd. It might be a good idea to say what that means. The next line should probably tell you what? Like, what is that? What line does that? Is this what it means to be odd?
No, that's what it means to be even.
Yeah, that's what it means. Is this what it means to be odd? No. What about this one? A is 2 times another number plus a bit. B is 2 times another integer plus a bit. That's the one. So this one is next. Right there. Now, sometimes when you write a proof, it's nice to put the end, at, like here, you know where you're trying to get, and then fill in the middle. What's the very last thing in the proof? What's our conclusion? Therefore, A plus B is even. And we use, this little box is like your treat for finishing the proof. You put it at the end. See, so I put our box here. Okay. So this is the proof shaping up. I still have to sort these three in order. So now your job is just these three. What order should they go in here to make a logical step-by-step argument that gets from the definition of odd to the fact that the sum is even? So what order should these three be in? That's what you should talk about. I made it bigger. Well, you want to go from the top down, or do you want to hook things up the top down? Okay, so we've established that this is A and this is B. What is it we're supposed to do to A and B? Add them up. What happens when we add them up? So what do we have? Two odd integers. What the heck does that mean? It means this. What do we want to do to them? We want to add them up. So what's next? These both say A plus B, which is it? The bottom one. Because I'm not concluding anything yet. I'm literally just taking the two pieces I had. See, A is 2k plus 1, and so that's here, right here. And B is 2j plus 1. I add them up, and then there's some just basic algebra. Okay. Now, why did we do that, though? Why did we factor this 2 out here? We didn't have to. That's right, because we want to prove it's 2 times, right? We want to prove that the sum is 2 times something. But actually, I'm going to put this here first because this quantity here that the 2 is multiplied by is an integer. And we've just written A plus B as 2 times an integer. See, here's A plus B. It's 2 times this thing. Well, what the heck is that? That thing is an integer. So A plus B has now been written as 2 times an integer. That is the definition of even. So A plus B is even. Once it gets in order, it should make a lot of sense to you that this is the order. I know it's really hard to put it in order, the first time, or even to write this proof if you don't have the pieces, right? That is a hard skill. We have a whole class for that in the math department. It's called 245. If you like doing that kind of stuff, you could take 245. If you're, who's computer science major? A lot of you. When you take 227, you'll be writing arguments like this and doing logic. It's like a mathematical, it's the computer science version of R245 in this department. So yeah, so you'll be taking 227. You're in 227 right now, Jerome. Is that true? Yeah. And you do stuff like this, yes? Yeah. I'm not lying. Yeah. Okay. So, and in our class, if you're reading the book, these proofs are all over the place. There's a theorem and then there's a proof about it. And you're not always responsible for those proofs. Some get pretty hard. But for select proofs, we will be thinking about it. Does anyone want to ask a question about this argument here? Okay. Well, let's go to the second part of the worksheet. The second part of the worksheet is about a counterexample. So here's a slightly different statement. In A and B are odd, starts out the same, but the wrong conclusion, right? In fact, it's really easy to find a counterexample to this because it's almost never true. It's actually never true, right? If you take 2 odd numbers and you add them up, you're never going to get an odd number. So not only is this false, sometimes it happens to be false for all pairs of odd numbers. So basically, any pair of odd numbers is going to be a perfectly good counterexample. These bits can be rearranged to make a sentence stating what the counterexample is. So try to make a coherent sentence. It's like those fridge magnets game. You know what I'm talking about, where the magnets have the words? Try to make that into a coherent sentence explaining a counterexample. I'm walking around and doing anything.
A plus B equals A. I don't know.
Well, I'll give you a hint sentence and usually start with a capital letter.
Oh.
So that's a hint right there.
You know, the first one is one better example. A plus B equals A.
I would go with A equals
But there's two of them. The separate ones are the. I feel like we put the formula. Yeah.
So what is it? What is a counterexample? What does that mean?
Example that disputes the claim.
Disputes a claim, right? And when you, that's exactly right. And when you have an implication, if A, then B, a counterexample makes A true, right? Satisfies the universe we're in, but it makes B not true, right? Makes B false. So I need an example that makes this statement true, A and B are odd, but this statement false, and I need to explain that. So what is the counterexample here? A equals 3, and that's not enough. I need A and B are odd. So what's the second part? B equals 5. Why is it a counterexample? Because you've only got 5 things to rearrange there. Finish this because. Oh, I'm sorry. Can I do this slightly differently? Yeah, sorry. Yeah, I'm going to do it this way. My apologies. That gives you a little more leeway.
Because it's odd.
All right, so I need this part to be true. Can you tell me why A equals 3, B equals 5 makes this true? Because A and B are odd. So that's not in here, but when you say it in the longer way it is, A equals 3 is odd and B equals 5 is odd. All right, so that's what I'm going to put. Because A equals 3 is odd and B equals 5 is odd. But what? A plus B equals 8. Not odd. This is how you want to write your counterexamples. My counterexample is this thing, because this thing makes the first part true and the second part false. That's what this statement is saying. My counterexample is A equals 3, B equals 5, because both of those things are odd, so this first part is true, but their sum is not odd, so that thing is false. Notice I said more words than what is said on the board, right? But it's clear that when you talk about the counterexample, you're exhibiting why the first part is true, a counterexample to an implication, why the first part is true and why the second part is false. Okay, and now if you read that sentence now, you could imagine if I originally said, is this a false statement? And why is it false? I might actually say this thing out loud, right? Like, well, 3 is odd and 5 is odd, but their sum 8 is not odd. So the statement's false. That's exactly how you explain that a statement is false, is by examining a counterexample. Okay, so, but notice that to prove something is true takes some serious work, because you have to prove it's true, not just once or twice or as many times as you can think of, right? But all the time for infinitely many things. And so you actually need an abstract general argument. That's hard. To show an implication is false, you just need one time that it's false and to point out that it's false at that one time. That's actually way easier. So if anyone ever says like, prove or give a counterexample, you're thinking to yourself, please let there be a counterexample because it's so much easier to handle that. Okay, questions about this? Does anyone want to take a picture of this? Or if you read it down, I'm about to scramble it so that next time I come here, it won't be in order. So I'll give you a minute to take a picture if you want. All right, I wonder if I can scramble it just by how far is the undo? There we go. That's pretty good. All right. Okay, so let's make another proof, but about something fun. I think one way to think about proving things is to, like, you convince yourself of something and then you have to convince somebody else. You have to make an argument. So what I have here is a logic puzzle. There's 3 people, and each of them, weirdly, either always tells the truth. Literally everything they say to you is true. They would never lie. Or they're a liar, but not just some of the time, not just strategically, all the time. So they're compelled to say a lie to every question or in every statement. Has anyone heard of these puzzles before? They're called truth liar puzzles. If you like these kind of puzzles, there's whole books of these puzzles that you can buy, like for fun, like the way you buy a Sudoku book and you play Sudoku, people buy books of truth liar puzzles. Sometimes they're called knight and knave puzzles. Sometimes there's knight, knave, vampire puzzles where the vampires have different rules. Sometimes some people switch from being truth tellers to liars. There's a whole thing, books and books and books about this, but this is just one, okay? So Liz, Rain, and Zubin, each one of them is either a truth teller or a liar, okay? Your job is to figure out which one of them are liars, if any, and which one of them tell the truth, if any. Okay, so the answer to this problem might be Zubin and Liz are liars and Rain tells the truth. Or Rain and Liz tell the truth and Zubin's a liar, stuff like that. Okay, that would be the solution to this puzzle. And there's enough information in what the people tell you to figure it out. So I would like you to get at the blackboards for this one and argue with each other about what you think the answer is. What I want you to write on the board is a convincing argument that would convince someone else. Like if you wrote a letter to somebody and you needed to convince them your answer was correct, what would you write? That's a hard problem, but we're going to give it a try. So this board, 2 at the back, 2 here, however you like. People in the middle, your choice, wherever you want to go. Yeah.
I can just say they're all liars and be like, I want it. I prove it. Yes. You can't trust the person who says, oh, he's automatically lying. And then when he gets I'm not saying it's logically saying this for him to not be lying, they all have to be think about it. We all tell us.
Ooh, I like
I mean, all of them have to be lying. They're either all truthers or they're liars. So it's an all or nothing kind of concept. So if you can figure out his lying, it's like a pyramid thing where it's like 3 dots, 3 dots.
I would say one of them might be.
One of them is saying we all a lot of that one is saying they all lie. Then the middle one is correct.
Nothing says they all lie.
I'm saying like if this one here is accurate, then this one is false, which makes this false.
Oh, you're right.
If they all lie, then this is false. Because this person is telling the truth. And so, well, actually, it's not possible.
None of it makes sense. Logically.
Okay, so I think.
You could be lying about it. Yeah, I just. You could be lying about
It
people.
should give you credit. That's all about everything everyone has told you to be a lie. How you do it. I don't want to go that far. This year is pretty bad for stuff like that. I don't want to go that far.
No, she's right. Because so if they're both, if both listen rain or shade, the other guys that come in the car, then they have to lie. I have it, right?
And rain would have to be. He's saying that
I do lies because they have a
So
code
maybe
about.
what we said is I'm telling the truth to someone else.
But no,
These
Well,
two,
what if
but you've been
this
saying
one,
that rain is only
if
lie.
she's telling the
he's
truth,
saying that they both live in lie, but they're both.
which means that one of them is telling the truth.
then that contradicts.
This is
That's right, so this doesn't. That makes everyone.
This is Zuby.
That's,
So there's not.
so what do you conclude about this?
Yeah, but that's just from you.
She can't be telling the truth.
And this is great.
And so you're like, contradicting.
This is great. That's great. And then this is Liz. Because it's like, yo, everybody's cool. And then this one is like, at least one person asked me.
And look, so if this statement was true, then that means that.
Anyone you can hit solving a puzzle.
Why? If it's true, then it's false.
You're not, you're not.
Because the other shit was really good.
Okay, I listen.
But if Zubin is true, if what he's saying is true, then that would make.
Because,
You know, it's wrong that she said we all tell the truth. So if he's lying, it's not wrong.
Well, this is always a lie. Because the following line.
Because she's saying we all know.
This is definitely a lie. I capped text.
I'm saying that those of them are lying.
Right.
The rest of them just said that all three of them are true.
Well,
Yeah, this one's got this had lines.
So like, it's nothing saying that she's really not
okay, what about race?
So Ray's saying that she.
I see what you mean. I see what you
So
mean.
Ray's saying.
Ray is saying that she would tell the truth.
But Ray's already out. So that means Rain is also.
Rain would have to be correct.
I like it. I like it. I get it.
And
All right. So how can we make this?
I have no idea.
And then,
Oh wait.
Now we have to.
that,
Hopefully don't make your own.
Liz can, I mean, race.
Better be.
No way.
Liz is telling the truth, but all the things that are mixed. So what's the truth you can make for
Alright, let's say suppose.
that? Liz is,
I love how Ray.
Liz is my name's my.
Suppose we have some rain.
Suppose Rain. I don't know how that works.
I think it's easier to start with Liz. Because if she's telling the truth, then everything's a contradiction. That can't be right. So you out of the gate, you know Liz is a liar. But I think that's the easiest thing.
This is gonna end up being a whole paragraph.
With a farmer's market.
Like what? Like if I say sky red, it's sky red. So you have to pick apart at least one. And in fact, you're gonna. Oh.
That would make.
So tiny. I'm coming over here to read your tiny.
Well, yes, but actually, no.
Liar.
You're a liar. The part that I don't understand is if Zubin is lying, I'm gonna cut it. I want to be lying. Yeah, she's lying. Oh,
Did I say and because?
I was like, I was back around.
All right, I'm going to stop you there, even though not everyone is done. So let's just talk about what we have here. Who's telling the truth? And are the other two people telling the truth, or are they lying? They're lying. Who can tell me why Liz has to be a liar? Why is Liz a liar?
I wrote it.
Well, Liz.
I like suppose Liz says everyone, you don't even have to suppose it because she does. So I wouldn't say suppose. If Liz says everyone's a truther, then everyone would contradict each other. We could elaborate, right? But if she says everyone tells the truth, well, if Ray is telling the truth, then that's already contradictory, right? Like, and if Zubin's telling the truth, well, that's also contradictory. Because Zubin says Liz is a liar, and we're supposing that she tells the truth. So we suppose that Liz tells the truth, and that leads to a catastrophe. This is called a proof by contradiction. Therefore, Liz has to be a liar, because if she told the truth, everything falls apart. So now you know what Liz is, right? And then who can take us a little bit further than that? What about Rain? Can Rain tell the truth?
Rain is also lying
Because it would contradict Zubin's statement.
yes.
Right, okay, so Rain's also lying.
So then if Rain is telling the truth, there's only one that's correct. So that's just.
Right, because we're assuming he tells the truth, so he's one of them. If the second one is Zubin,
Then that Zubin's saying.
contradiction, right? And if the second one is Liz, contradiction, we already established she's a liar. So Rain's a liar. And then when you look at Zubin's statement, you're like, yep, that's what we just figured out. So he's telling the truth. Now, part of this I wanted to do just because it's fun, it gets you talking, gets you thinking about something logical. But also, for some reason, it's so much easier to write up a proof when there's no algebra or math or calculus in it, right? We're just talking and making an argument. That's how you want to think about the math proofs in this class, right? When you see a math proof, there's going to be tons of symbols and all this stuff, just like we did in the Miro proof. There's going to be this business, although not written in this kind of shorthand. But really, you're just trying to make an argument that convinces everybody. You're trying to get your facts in order, right? And make a convincing argument. Okay. All right, so there, if you like puzzles like this, there's probably a bunch that are free online if you don't want to buy them. I want to remind you again that the second half of this section has to do with reviewing the chapter, which includes rules of fractions and all of this notation. The end of every chapter in the ebook ends with a list of the notation and basic skills you should have by the end of the chapter. It's a really good way to review. Again, you're going to need to review things like simplifying, solving inequalities, solving equations, finding domains, graphing transformations, all those basic skills. Because if you think about it, we all came in at different places, right? We all had different backgrounds, different classes, and different confidence with this material. And the whole purpose of this first 4 weeks is to get everybody to the same place, okay? So make sure this week that you feel like you've gotten to that place, okay? And if you need help, there's 3 things here. First of all, Jerome, of course, is still running past sessions on Tuesday and Thursday nights at 6:30 in this very room. There's plenty of seats left for people to come. It's very helpful. He's been making worksheets about the material, right, that are helpful. Do you want to say anything about it? Please come. Yeah, you can, it'll be great. You should go. This is very valuable. And there's a new thing. So in my other section of calculus, we have a different kind of TA. Instead of a path reader, we have something that's called a math and stat learning assistant. And these 2 roles are somewhat different, but we're making it so that both sections can go to both things. So you actually have a lot of opportunities. Sarah is the learning assistant for my other class and also therefore for you. She is holding sessions on Monday nights in the room down the hall at 6 o'clock for those people who are struggling with algebra, struggling with chapter 0, who were sick during many of the first couple weeks and have trouble catching up. So if you're having trouble getting your footing, if you're having trouble with the algebra, if you're having trouble with chapter 0, then she'll be here on Mondays to talk to you about that, okay? And you can get help from her on those days. And finally, the Math and Science Learning Center is open in person from 10 to 6 on Tuesdays, Wednesdays, and Thursdays. So that means anywhere starting literally right now until 6 p.m., you can go to the Student Success Center. You can sit down and do your work there. There'll be a tutor right there to help you. I highly recommend going to work in the Science and Math Learning Center. It's super valuable. And I just want to check something really fast. Okay, fine. It's super valuable. And in fact, what I'd like to do is take the last couple minutes of class for you to talk to people at your table or at the next table, and maybe make plans to go down to the SSC, is that what it's called? The Student Success Center. We didn't used to have that. And go to the Learning Center, check in, see what it's like. Maybe do a little bit of work. You can eat over at that Bistro 19, whatever it is. What's it called? There's like a place to eat. Bistro. It's right next to Diet here. That place is nice. Yeah. So, okay, last couple minutes, talk to your neighbors. Maybe somebody will go over there with you today. Okay? All right, have a great day. See you Friday.
Have a good evening.
Have a good day and evening.